guest of honor, and beloved professors and my dear friends. Warm welcome to everyone. I am Dr. Elil Raja from Department of Mechanical Engineering. Welcome you all to the 5 days FDP on metal additive manufacturing from advances to adaptability. Before we start this faculty development program, on behalf of the Department of Mechanical Engineering, St. Joseph Institute of Technology, I would like to welcome our chief guest, Dr. Jinoop Arackal Narayanan, Assistant Professor, Teesside University, United Kingdom, for spending his precious time with us. I would like to welcome our respected principal, Dr. Arivalagan, for giving us their consent for this program. And I would be a great pleasure to welcome the Dean, Dr. Sri Kumar, for his support to conduct this program successfully. I would like to welcome all the professors act as participants today from various institutions throughout the country. Definitely, I assure that the program, this FDP, will be very useful for you to understand the metal additive manufacturing from advances to adaptability, and it will be useful to disseminate the knowledge that you have gained here to the student community. So without you, this program will not be a successful one. Once again, I welcome you all. Thank you.
Okay, thank you for welcoming address, sir. So let me invite Dr. S. Arivalang, sir, Principal, St. Joseph's Technology, to brief about the FDP topics and need of the topic for this hour. So welcome. Principal, sir.
Good evening. Good evening. Yes. Am I audible?
Yes, sir, audible.
Am I audible?
Yes, sir, audible, sir.
Yes, sir.
Yes, sir.
A very good evening to Dr. Jinoop Narayanan, Chief Guest of today's FDP program. It is a 5-day online FDP program arranged by Department of Mechanical Engineering, St. Joseph's Institute of Technology. I congratulate the department for having thought of this idea to organize an FDP for 5 days, inviting eminent faculty members from reputed universities and institutes in India as well as abroad. We thank the Chief Guest, Dr. Jinoop Narayanan, for sparing his valuable time to be with us to share his expertise in the field of additive manufacturing. This 5-day program will cover different topics in metal additive manufacturing. To start with, today we have metal additive manufacturing of advanced materials being delivered by our Chief Guest today, followed by laser additive manufacturing to be delivered by Dr. C.P. Paul from Indore, and extrusion-based metal additive manufacturing by Dr. Pratik Saxena, IIT Mandi, followed by digital fin in additive manufacturing by Dr. Sindhil Kumar, TDM Kanjipuram, and wire-based metal additive manufacturing, lecture to be delivered by Mr. Sajan Kapil from IIT Guwahati. All the participants from various institutes, various universities and institutes from India and abroad will definitely gain expertise in the field in this series of 5-day FDP programs. I wish a happy learning for all the participants. Once again, I thank all the speakers and especially today's Chief Guest, Dr. Jinoop, for sparing his valuable time to deliver his lecture on this topic. I thank all the coordinators of the event, Dr. Edil Raja, Dr. Emmanuel, and all the faculty members who are coordinating this event. I thank our management for facilitating this type of events for the benefit of faculty members from all the institutes. Wish you all a happy learning. Let me invite Dr. Jinoop to take over. Thank you, sir. Thank you.
Thank you very much.
Sir, before 1 minute, we will introduce you, sir, to the participants.
Thank you.
So I invite Dr. Crispin Das to share a few words about the Chief Guest today. Crispin, sir.
Very good evening to one and all who are present here for this 5-day online faculty development program on metal additive manufacturing from advances to adaptability. We have our guest, Dr. Jinoop Arackal Narayanan. He has completed his Bachelor of Engineering in Mechanical Engineering in the University of Kerala. Also, he has done his Masters in Additive Manufacturing from NIT Warangal. Also, he has earned his PhD in Laser Additive Manufacturing from Homi Bhabha National Institute, Mumbai, India. Also, Dr. Jinoop Arackal Narayanan is a fellow of Institute of Materials, Minerals and Minings and a lecturer in Mechanical Engineering at the School of Computing Engineering and Digital Technologies, Teesside University, UK. Prior to this role, he held positions as a research fellow in additive manufacturing at the Welding and Additive Manufacturing Center, Cranfield University, UK from January to June 2023, and as an industrial postdoctoral researcher at the Multi-Scale Additive Manufacturing Lab, University of Waterloo, Canada from 2021 to 2023. He also worked as DAE Research Fellow at the Laser Additive Manufacturing Laboratory at Raja Ramana Center for Advanced Technology, Indore, India from 2016 to 2021. He has more than 90 publications in the field of additive manufacturing, including journal papers in peer-reviewed international journals, book chapters, international national conference, paper presentation. Also notably, he authored the first comprehensive textbook on additive manufacturing in India, published by McGraw-Hill Higher Education for UG and PG scholars. Additionally, Dr. Narayanan serves as an editor and reviewer for several reputed international journals. His contribution to the field have been recognized through various awards and fellowships. In 2019, he was honored with the Young Scientist Award in Mechanical Engineering by the Madhya Pradesh government. Subsequently, he worked as an Young Scientist Fellow at Vikram Sarabhai Space Center, Trivandrum, focusing on metal additive manufacturing. He has also been awarded the Best PhD Thesis Award from the Indian Laser Association, and his works have received Best Paper and Poster Awards during the national conferences and technical events. Also, he has received fellowships from Ministry of Human Resource Development and Department of Atomic Energy, Government of India. Dr. Narayanan is actively involved in several collaborative projects related to metal additive manufacturing with several international universities, research labs, and industries. Also, he has he's been reviewing various journals, and he is also an editorial board member of various journals. We are very happy to have you, sir, for this 5-day online FDP program. And for the first day, we are happy to have you here for this session. I hope it will be a very useful session for all the participants who are present here. Thank you.
Thank you, sir, for your introduction. So participants, please mute your mic. Towards the end of the session, query session will be there. At that time, we can unmute and ask your queries to the speaker. And you can post your questions in the chat box also. It will be addressed to you. So over to you, sir. So Dr. will continue the lectures. Thank you.
Thank you. Can you see my screen?
Yes, sir.
Yes, Professor. Yes.
Thank you. Yeah. So, good evening, India. So, good evening to all. First of all, thank you very much for this opportunity, and thank you for me as a guest in the first day of this session. It is an honor to be here, sharing knowledge on additive manufacturing with the participants, with the faculties and students everywhere. So my name is Jinoop. I'm a lecturer in mechanical engineering at Teesside University in the UK. I'm also an adjunct professor at Satyabama University in Chennai. So the topic for today's discussion is metal additive manufacturing or advanced materials. So I'll just give you these are the just presentation plan for the lecture today. So first I'll be introducing the university, just a brief about that. Then metal additive manufacturing, just basics, since this is the first session of this particular FDP program. It will be worth discussing some of the basics of additive manufacturing. Then we'll go to the research on metal additive manufacturing, something that I have done in the past, and some of my ongoing research works and conclusions. So, as mentioned previously, this is a textbook on additive manufacturing, which we have prepared in 2021. It's authored by Professor C.P. Paul and myself, Professor C.P. Paul is going to deliver the session tomorrow. So we both have completed this textbook and published by McGraw-Hill Higher Education in 2021. And it's a textbook that covers the whole range of additive manufacturing, from the process, from pre-processing, from the basic stages to the advanced stages. And it's a textbook which is tailored for the Indian education, the way our syllabuses are framed. So it will be worth reading this textbook if you have not done it previously. And if you have done it, then I'll be appreciate if you could share the feedback. So because we are working on the second edition of this textbook, so it'd be worth getting the feedback of the readers before we go on to the second edition. So I'd suggest if you can go through this book and give us the feedback. So coming to Teesside University, Teesside University is one of the leading young universities in the UK. It is located at the northeast of England, as you can see in the map. You can see in the map, it's the northeast part of England, and it is between Newcastle and Leeds, which are the major cities in the UK. It is ranked in top 6 in mechanical engineering by Guardian University Guide, and it is a triple gold university in terms of student satisfaction and student outcomes. And coming to the university, so this is how a university is. So this is our library and the one of the oldest buildings in the university. And this is how our town is. So it's a small town in the northeast called Middlesbrough. So those who are following football might be knowing Middlesbrough in a better way, because Middlesbrough Football Club is famous. So you can see this is, and we are located very close to the sea. And we have 5 different schools in the university. Starts from School of Arts and Creative Industries to School of Health, School of Social Science, and we have the Business School. I come from School of Computing, Engineering, and Digital Technologies, where I'm assistant professor at the moment. And this is one of the biggest investment of Teesside University. So this has to go with advanced manufacturing, additive manufacturing as well. So that's why I brought into this. So we have a net zero industry innovation center at Teesside University, it's a 13 million pound investment by the UK government, Teesside University, and the local council. So we are trying to develop a center which works on net zero applications, trying to decarbonize the industries in the UK. So we basically work on hydrogen, decarbonization, circular economy sort of research in this center. And we are now working on 11 million projects supported by Research England for supporting hydrogen innovation in the Tees Valley. Basic idea is to decarbonize the sectors in this area. So this is how AM is at Teesside University. We have polymer 3D printers. We have wire arc 3D printer, which is a dual torch wire arc 3D printer, which I don't have a photo at the moment. That's why I put a schematic at this point. And I have a multi-material 3D printer, which works on clay, ceramic, and concrete, which can be used based on extrusion philosophy. Then we have wide range of polymer 3D printers as well. So we have printers in material extrusion, material jetting, fat photopolymerization, and DET-based metal additive manufacturing, and material extrusion. So we cover a wide range of processes at Teesside University. We are in the process of expanding further to more laser-based systems. And we have a Siemens connected curriculum at Teesside University. So we work with Siemens on the software packages. So we have NX, and we have the different design softwares associated with Siemens, which can be used for design for AM, tooth planning, etc. So now let's go into the topic. So let me start off with what basics of additive manufacturing. So additive manufacturing is defined as a process of joining materials to make parts from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing and formative manufacturing methodologies. So this is the basics of additive manufacturing, if you say the basic definition of additive manufacturing. And when you start dividing it into different aspects, you can see that first is a process of joining of materials. It starts from a 3D model data. It involves layer by layer material build-up approach, and it's not a subtractive technology, and it's not a formative manufacturing technology. So it means that the material addition happens in a layer by layer fashion. It involves joining of materials, starts from a CAD model data or a 3D digital model data, and does not involve subtractive or formative manufacturing methodologies. And if you start giving the understanding the different names of this technology, so the most commonly used name for this technology is 3D printing. Again, most of the people might be knowing rapid prototyping because it was used in the technology was initially used for prototyping applications. So 3D printing, rapid prototyping, rapid manufacturing. Then again, different names came into existence like additive fabrication, layer manufacturing, freeform fabrication, additive techniques. But in ASTM standardized all these names into a single name, which is known as additive manufacturing, which is the industry standard name for this technology. So people just get confused sometimes between 3D printing and additive manufacturing, but it's both are one and the same. So what is it actually? Just a basic idea of what is 3D printing. If we just have a comparison with our normal 2D printing. So we have a image or a document on our computer screen, and we're taking a printout on a paper using a normal printer. So our input data is the 2D drawing or the document that we are trying to print, or our raw material is the paper, and the ink or printer is the system that converts this image or into a particular printed drawing. While in 3D printing, it's almost similar, but only difference is that everything is in 3D. So instead of using a 2D image or a document, we use a 3D model data here as an input. Instead of using a paper, we use our uh, filament as a raw material. Then instead of using a normal 2D printer, we use a 3D printer, which can add materials layer by layer. And at the end of the day, we have a 3D part which is produced. So it's very similar to 2D printing, but in a different scale and a different dimension. So it's similar to how a basic natural growth happens. So it's similar to how a plant grows from a seed to a completely grown tree, or it's how the layer by layer addition of bricks happens in the construction of a house. So it's a natural process, and all these details we have given a lot of details of this in our textbook on additive manufacturing. Feel free to read it if you want to have further discussion on further understanding of this. So additive manufacturing is a very natural process, but technology was not there at the earlier stages to convert it to an industrial product. But as the technology advanced, we could convert the natural process into a technology which can be used for the industries. Yeah. So the pre-processing stage is the first stage of 3D printing, where we convert our CAD model. We generate the CAD model. So we use a software like normal our CAD softwares or simulation softwares to generate a CAD model. So this CAD model is further converted into the system specific file format. So the most commonly used file format in 3D printing or additive manufacturing is STL file format. So we convert our CAD model to STL file format, and then we use AMF at the moment. So a lot of advances are happening in terms of the file formats as well, but STL is the most commonly used file format. So once we convert to STL, then we set into the system, and in the system we convert the CAD model into 2D layers. So suppose if you, and the most common example that I give is if you want to make a cylinder, and if you make a CAD model of a cylinder and we give it to the machine converts into number of 2D sessions, that is one number of 2D layers of circles. So this is generated by the system, then it goes to the machine, and the machine adds material in a layer by layer fashion. So the pre-processing stage is complete, and we go to the processing stage where the material addition happens in a layer by layer fashion. And once the part is produced in the processing stage, it goes to post-processing stage, where we try to do the treatments which are required with the customer. So suppose, for example, the customer requires a high surface finish or a high strength or a high different compressive stresses on the surface, we need to select the proper post-processing technique as per the customer requirements. So this is a stage where we can customize our part for the user, customize our structure for a user application. So based on this, we do finishing application, we do heat treatments, or we do support structure removal or painting. All these things will be done in this particular stage so that we get the final product, which is a 3D printed part, which having a better properties, which meets the customer requirements and the final requirements. So why is additive manufacturing very important? Just give me a second. Yeah. So why is additive manufacturing very important? Because additive manufacturing, you can see from the diagram itself that additive manufacturing helps you to build complex structures for free. That means in conventional manufacturing, if the cost of the if the complexity of the parts increases, then the cost of the part increases continuously. But at the same time, if you go for additive manufacturing, we can see that the complexity is not the cost is not a function of the complexity, and if the complexity of the part increases, the cost doesn't increase. This is basically the relation that is coming out from the CAD models. You can see here, if you have this sort of CAD model which is highly complex, with a highly complex part in a 3 dimension, once you start converting into different 2D layers, the complex design of these parts converts to simple 2D sketches. That means the complex design that we have converts into simple 2D sketches, that is circles and lines. And then we try to convert all the complexity in the 3 dimension into simple 2D sketches. When we try to simplify the complexity, and then we can have complex shape structures and without any increase in the cost. At the same time, the cost is directly not a function of the complexity. If we say conventional manufacturing or subtractive manufacturing, generally we need to change the orientation during the machining at multiple stages when we want to go for highly complex structures. But in additive manufacturing, since we are doing it in layer by layer fashion, we don't have to do that, and the material addition happens in a layer by layer fashion without any dependence on the complexity. So if the material requirement and the time remains constant, then the cost is not a function of the complexity of the part. Then again, additive manufacturing provides you material design freedom. That means you can, since you are building the parts in a layer by layer fashion, you can have multiple materials in a different layers. Even within the layer, you can have multiple materials. So it gives you material design freedom, which permits you to join uh, multi-material components or dissimilar materials, which permits you to go for functionally gated structures or dissimilar welding structures. This helps you to produce parts for diverse conditions. So let's take the example of a nuclear condition where we try to join stainless steel to titanium. If you have a titanium tank and if you want to connect it to a stainless steel pipeline, it's very difficult because titanium and stainless steel are not compatible with each other for welding. So if you start going for that, then going for additive manufacturing, you can build stainless steel and titanium joints by going for multiple materials. We can bring a friendly material in both of them, in between both of them, and try to join this dissimilar material. So it provides material design freedom. And again, the next part is mass customization. So additive manufacturing helps you to go for customization. At the same time, it can help you to go for large scale manufacturing. So if you have a single build plate and if you want to make multiple components in a single build plate, you can have different designs and you can have in large quantity as well. So if you take the example of this dental implants which are being made, so these are of different designs and we can make large numbers at the same time in a single build plate. So that's the advantage of this technology. Again, integrated components, we can integrate sensors during the manufacturing, which will permit you to go for smart components. So as per ASTM, these are the 7 different additive manufacturing processes. For this, powder bed fusion, then wet photopolymerization, material extrusion, material jetting, binder jetting, directed energy deposition, and sheet lamination. All these processes have their own advantages and limitations, and all these can be used for different applications. So general understanding is that any of additive manufacturing process can be used for any application. It's not like that. We need to understand what is the advantage and limitation of a specific additive manufacturing process so that we can select a process for any application. Suppose, for example, powder bed fusion uses powder as the raw material, where we go for very fine featured metal additive manufacturing parts. VAT photopolymerization generally use liquid as a raw material, along with material jetting, and these are used for making polymer parts which are very fine micrometer size. So we can go to micro size or nanometric size with these sort of processes. And if you want very precise geometries in polymers, we need to go for either VAT photopolymerization or material jetting. But if your requirement is to make a polymer part without without high accuracy, we need to produce a parts for verifying our design sort of thing, then we go for material extrusion. Binder jetting again is used using powder, which can be used for metal and polymer additive manufacturing. Sheet lamination uses sheet as a raw material, and sheets are joined one over the other to make the right components. And direct energy deposition uses wire or powder as a raw material, which is generally used for making metals. So in this particular presentation, we'll be discussing more about powder bed fusion, direct energy deposition, because since we are going to deal more about metal additive manufacturing. And some of these processes, as I mentioned, VAT photopolymerization, material extrusion, material jetting, binder jetting, are more commonly used for polymers, but they can also be used for metals. So this brings into another classification of metal additive manufacturing, where we can classify metal additive manufacturing into two, that is direct process and indirect process. Direct process is a process in which we can completely melt metallic particles and to join them together to make 3D parts. We use laser, electron beam, or an arc to melt materials so that we can join them to make a 3D part. At the same time, there is an indirect process, indirect additive manufacturing, where we cannot go for complete melting. So the process like VAT photopolymerization, material extrusion, material jetting, and binder jetting, where we can make a green part is a mix of polymer and metal. So what we do is we try to join the particles together and we try to make a green part, which is a mix of polymers and metal. So for take the example of a normal 3D printing process, we use a filament, which is a mix of metal and polymer. Metallic powders will be there and polymeric materials will be there. And we try to melt and join the polymeric materials together while the metallic particles or the powders remain as it is. They will not be melted or joined together. And once that is done, we go to the debinding stage. So we get a part which is a green part, which has got the shape that we require, but doesn't have the properties that we need. Then we go to debinding stage, where we try to remove these polymer parts and try to improve the density of it. So what we do is we try to remove these polymers by doing some exposing it to very high temperature. So it's called brown part. Then we go to the final stage of sintering process, where we try to increase the density of the parts by bonding the metallic particles together. So this is basically a metal additive manufacturing process, but in a different way. It doesn't use high energy density sources like laser or electron beam for complete melting, but we use something like a furnaces or a sintering stage, where we try to enhance the density of a polymer metal mix and try to make a metal part out of it. So this is more similar to powder metallurgy process, where the debinding and sintering stages are more similar to powder metallurgy. But again, the first stage is a green part, where instead of compacting in powder metallurgy, we go for printing stage. We try to generate the green part. This has been increasingly used in the industry nowadays. I had a opportunity to work on this when I was in Canada. I worked on a Markforged Metal X machine, which uses FDM principle, or the normal plastic 3D printing principle, to make metallic parts. So I worked on A2 tool steel as a material there. So A2 tool steel is a very hard material to work on in terms of 3D printing, and there was no process developed for other metal additive manufacturing processes. So the Markforged has A2 tool steel, which can be processed with that. So we went to that, and we could then get more than 90%, 95% density with this process at optimized conditions. So it's a very good process if we don't have to spend a lot of money on metal additive manufacturing, investing into metal additive manufacturing. There are a lot of systems available in the world in this particular systems, like Markforged is one of the example. Zerion from Germany is another example of a system that works on this philosophy. So we can use the normal polymer 3D printers for printing metallic parts if you are using this sort of philosophy for metallic making the parts. Let's go more deeper into metal additive manufacturing. So the most commonly used metal additive manufacturing process are powder bed fusion and directed energy deposition. Powder bed fusion, as you can see in this video, we use a laser beam to selectively melt a region of powder bed, and you do it in a layer by layer fashion. So the spreader spreads a layer of powder, then the laser selectively melts a region as per the requirement. Then you do it in a layer by layer fashion to make a final part. It has got a lot of advantages and it's one of the most commonly used metal additive manufacturing processes. So it uses laser to fuse the regions, or laser electron beam is to fuse regions of powder bed. It builds parts of unlimited complexity. That's why it is one of the most commonly used metal additive manufacturing process in the world. Because whenever you want to make highly complex design by 3D printing, whenever you want to take the complete benefit of using 3D printing, you need to go for this technology if you want to use it for complex shapes. And it has lightweight structures. It can go for thin feature fabrication because the feature size can be in micron scale, so you can print parts in micron scale with this technology. Directed energy deposition is another process which uses laser, electron beam, or electron arc source for melting materials. We have a similar system here. I have worked a lot on these systems during my different research tenures. So worked on laser-based systems and arc-based systems. So we use the energy source to create a melt pool onto which you add the material and you deposit material in a layer by layer fashion. That is directed energy deposition. And it is very commonly used for repair and remanufacturing applications. So we can use this for turbine blade repairs or repairing of the mold or toolings in industries. It's used for functionally graded structures. So we discussed about material design freedom some time back. So this technology can be used for joining multiple materials or dissimilar materials, and we can use this for high build rate. We can use it for near net shape manufacturing. We can use it for complex shapes. So a lot of applications. We'll discuss more details as we move forward. So we can see that two basic raw materials that we have seen in metal additive manufacturing. One is powder, another one is wire. So the basic advantage of using wire. So let's break this down into two. Let's go with first wire. And if you start understanding why wire is really important, because wire basically uses something which is in the millimeter scale. So there is no safety issues associated with the wires. So the major issues, that major problem associated with powder is a safety regulation. So that's why many of the industries or many of the countries are, or the universities have very stringent rules when it comes to metal additive manufacturing, because powder handling is really risky, because all these materials that the ink corners or the nickel based superalloys that we work with have chromium and content in that and different other elements which causes cancer. So it's very difficult to handle these sort of materials. There should be a stringent control, a safety control when you want to use powders for additive manufacturing. So that's one of the major limitations of going with powder. And so why does it have that problem? And at the same time, if you go for this sort of process like directed energy deposition, if you feed powder, not all the powder is captured by the melt pool. So the typical catchment efficiency, is nothing but if you if you add 100 grams of powder, how much powder is converted into final product? So typically the catchment efficiency in powder direct energy deposition, if it is powder based system, is its maximum ranges up to 70 to 80%, and typical value is 50 to 60%. So you lose a lot of powders which can be anyway recycled to and use it again. But we tend to lose a lot of materials during the manufacturing. We'll not be able to capture all the raw material to the deposition. That's one of the major limitation of going for powder. But at the same time, if you go for wire, if you start feeding wire into it, we'll not be losing wire, and almost all of the wire will be converted, melted and converted into the final structure. So wire-based additive manufacturing gives you almost 90 to 99 to 100% material catchment, while powder-based additive manufacturing has a limitation in terms of the catchment efficiency. And when you're going to go for high resolution, when you want to print multiple materials, when you want high surface finish and dimensional accuracy, you tend to go for powder-based DED than wire-based additive manufacturing. So this is the pros and cons of this technology, and powders are really costly as compared to wires. So there are a lot of differences, a lot of advantages and limitations for both. So whenever you select a process for your application, You need to understand what is your requirement. And suppose, for example, in a case where you want to make a very fine featured structure, you cannot go for wires, because in wire, the basic raw material size itself is 0.8 millimeter to 1.2 millimeter. So micron scale deposition is really challenging when you go for wire-based ready manufacturing, even though we have micro wire DEDs available in the market. But the most common ones for those sort of applications where we need to go for micron scale is powder bed fusion or powder-based ready manufacturing. So let's discuss both the processes in more detail. So if you go for powder bed fusion, as I mentioned, the shape complexity is very high. We can go for fine features. It has high mechanical strength because of high cooling rate involved and fine grain structures. Dimensional accuracy and surface roughness is very good. Powder means surface roughness is very low and we have high surface finish. Powder reusability, we can reuse the powders for manufacturing. That's one of the advantages. Limited multi-material capability, porosity, low build rate, and build volume is the limitations of the technology. So in terms of powder bed fusion, normally we tend to have smaller systems. Nowadays we have systems in meter scale as well, which goes up to 1 meter or 2 meter size. But generally, DED has more built volume as compared to powder bed fusion, because DED uses a nozzle which is attached to a CNC or a gantry, and so we can move the larger, we can cover larger areas and we can print larger structures by using DED. But in powder bed fusion, since we are using a smaller system, within the system limitation we need to work on, so we cannot go for very large structures by using powder bed fusion. It's used in aerospace, it's used in medical, it's used in tooling sectors, and used in automotive a lot. And wherever we need to go for lightweighting or design complex structures to make the lightweighting requirements, we need to go for powder bed fusion. The most commonly used process parameters in powder bed fusion are laser or electron beam power. So the laser power or the basically beam power that is used. So scanning speed, the speed at which the laser is moving. Layer thickness is nothing but the thickness of the layer that is spread by the powder spreader. Hatch spacing is the overlap between two laser tracks. So this is one laser track and this is another laser track. What is the overlap between them? So that's called hatch spacing or line offset. Then the beam spot size, that is a diameter of this beam, laser beam that's available on the substrate surface. So these are the different process parameters used in powder bed fusion, very commonly used process parameters. Again, we have multiple other process parameters involved in it, but these are the most commonly used ones. And all these are, the first four are connected by a term called volumetric energy density. So volumetric energy density is nothing but the ratio between power and the product of scanning speed, hatch spacing, and layer thickness. So this gives you something in the range of joule per meter cube or joule per millimeter cube as the amount of energy required to melt a volume of material. So this volume, this energy density, volumetric energy density, is something that controls the quality of deposition when you go for powder bed fusion. So you can see how important is the process parameters. You can see a graph between laser power and scanning speed here. Just by varying the laser power and scanning speed, we could move from one zone to other zone, and we could end up move from overheating zone to a zone where we could have complete melting to a zone where we end up in cracking and process issues. So it's very important to control these parameters. You can also see here laser power and scanning speed. If you go for this sort of area, we end up in different properties. While this is an optimum energy density contour where we can get very high density. So it's very important to control these process parameters and find a range where we can produce parts of very high quality. And if you start comparing, see, if as I mentioned, this laser energy density unit is joule per millimeter cube. So if we can calculate and try to find a relation between laser energy density and the relative density, we can find that as the laser energy density increases, the density of the part increases, because at a lower energy density, the lack of fusion happens. The material will not be having sufficient energy for complete fusion. So we end up in very high porosities at lower values of laser energy density. But as we increase the laser energy density, the density of the part increases, and we end up in parts having very high density, typically close to 100% density nowadays. And as we increase the laser energy density further, then we can see that the relative density decreases again. This is because as we go to very high laser energy density, there will be loss of elements, there will be gas porosities, keyhole porosities happening, which results in reduction in the density at higher laser energy density values. Then coming to direct energy deposition process, so we have, as I mentioned, we use a laser, we use a material feeder, which can be powder or wire. In this case, we use a computer to control it. We have a CNC table, and we can remove the CNC table with a robot, or we can attach to a gantry. Basically, we use a deposition head, which is a major key of this particular process. So the major heart of this process is the deposition head, which controls the quality of deposition. You can see how complex is this deposition head. You can see that there's a point port which gives the shielding gas. There's an area which focuses the powder. There's a focusing lens which adjusts the laser position. So all these plays an important role in controlling the quality of the deposition. And then we can control the movement of in the XY direction by moving the deposition head or by moving the table. So basically, by controlling this process, we would be able to deposit the material. So you can see here, this is a slot where the powder comes in. This is a slot where the shielding gas is used. Basically, we use argon as a shielding gas in most of the cases, which is just to prevent the oxidation of the melt pool. Powder is always carried by another carrier gas, which is again argon in most of the cases. So argon has two functions. One is to carry the powder to the melt pool, and the other one is to protect the melt pool from oxidation. So these are the two advantages of using argon and as a shielding gas and as a carrier gas. So then the laser creates a melt pool on the surface onto which this material is added, and then we get a deposition. So we can use powder, and at the same time we can use wire as well. So this system is a system which is developed by Fraunhofer, and they uses a laser and a wire. The wire is fed from the sender. The laser is split into three. So one part of the laser goes here to mirror one and gets focused on this point. Then again, the second part of the laser goes here, focused on the surface. Again, 33% comes here. The last portion of the laser comes here and focused on the point again. So the laser is split into three halves, three parts, 33% each. Suppose we take the example, 3000 watt is the laser power. You convert into three laser beams of 1000 watts each. You focus at a single point where the wire comes and you melt it and deposit it. So that's how the coaxial wire feeding based DED works in laser based DED. Then again, we have lateral based systems. So I had a opportunity to work on this when I was in Cranfield. So we use laser from the center and we use lateral feeding of wire from the side. So the major limitation of this process is the control. So we have a lot of advantage of using wire, but the major issue of using wire is the positioning control of the laser beam and the wire. So the wire position should be specifically controlled to ensure a quality deposition. While in case of powder based DED, if you have the nozzle designed and if the nozzle can focus the powder at the right location, then controlling the quality, controlling the positioning is not a issue when we start depositing it. But when you use wire-based DED and specifically the lateral DED, the controlling the position is really challenging. So controlling the position is very important, and there can be multiple positions where you can do the deposition, and it's very difficult to control it. And we need to have a proper optimized window to develop the high quality deposition. Again, it has similar electron beam DED is another part of it, and as you know, wire arc additive manufacturing is something which is an extension of welding. So gas metal arc welding and gas tungsten arc welding, we use TIG and MIG welding and plasma welding for additive manufacturing. So instead of using laser or electron beam, we use wire arc, the plasma arc, or the tungsten arc, or the MIG based sources to melt the material and deposit it. So it's being used a lot nowadays, basically because of the high build rate it can achieve. It can go for multiple materials. It can be used for large scale deposition. And most importantly, it can reduce the build time significantly. So when you want to go for large scale structures, we tend to go for wire arc additive manufacturing. One of the exciting applications that people are working on at the moment is storage tanks made of hydrogen for hydrogen transportation. So storage tanks which are made of steels or titanium can be made of this sort of technology. So using wire arc additive manufacturing, so that we can reduce the material wastage significantly, and you can make high quality structures and go for machining. And later on, we can reduce material wastage significantly by going for these techniques. Again, the advantages of DED, so high deposition rate, we can go for dense and strong parts. So almost 100% density can be achieved by DED processes. Multi-material range, so we have seen that we use powder feeders in this, so we can tend to have dual hopper feeder, so we can have multiple materials in the powder feeder, so we can vary. For example, let's take A and B are two materials. We can vary the composition between A and B. We can have 50% A, 50% B, or 75% A, 25% B, and we can have variation in the composition. So by using dual hopper powder feeders, we can see two hoppers here. And at the same time, in terms of wire as well, we can use dual wire feeders to get multiple materials. So multi-material is one of the important applications of DED. We can go for larger parts, as I mentioned. We can attach this nozzle to a gantry, to a robot, and we can go for large scale structures. We can easily change the material as compared to powder bed fusion, and there's reduced material wastage as compared to powder bed fusion, because the major reason is in powder bed fusion, you spread a layer of powder, then you use a laser to selectively melt a region. So if you spread a region of 100 by 100 and you want to make a part of 50 by 50, then the rest of the material is wasted, or you want to recycle all of the material again. But in DED, since you're adding material only at the points where it is required, the material wastage is very much less as compared to powder bed fusion. That's one of the major advantages. Coming to limitations, so as every process has their own advantages and limitations, DED is not generally used for very high surface accuracy. So if you want to make parts in micron scale, DED is not the process, but instead we go for powder bed fusion. There's limited shape design freedom as compared to powder bed fusion, and there's thermal distortion because of the high heat energy that we are using. So if you go to the advantages of technology, there are multiple advantages, like some of them I already discussed: large scale manufacturing, multi-axis deposition. We can use wire or powder, where in powder bed fusion, we can use only powder, while in DED, we can use powder and wire. We can use multiple materials, as I mentioned. We can have multiple feeders. We can have different combination of materials. We can use it for multi-material structures, coatings, alloy design. We can make new alloys. We can go for repair and remanufacturing application. High deposition rate, because we tend to use lasers in millimeter scale, not the micron scale lasers. Integration of secondary processes. So if you see, most of the hybrid additive manufacturing systems will be DED based. So they'll be having a machining center attached to it, and we have milling cutters attached to the DED system. So once you go for the deposition, then you can go for the machining application at the same time, which can be used for improving the surface quality. Then large area cladding. So as you can understand from this, laser DED is nothing but an extension of cladding process. So you can go for large area cladding with this process and go for deposition of superior material over inferior materials. This is one of the applications which I worked on. So this is one of the case studies on repair and remanufacturing. So when I was working in Canada in the industry as a postdoc, during the assembly manufacturing, one of the product got broken, and we need to produce the parts at the which in a short turnaround time. So one of the requirement was to build on top of it. So there's a tool steel material. So we then scan the part, we design the product, we develop the process, and then we deposit on top of it, and we could return it back to the customer within 24 hours of turnaround time. So if you see this sort of application, so I'll show you some more application in the later slides. You see these sort of applications where the turnaround time is very less. We need to produce parts instantly. Then we can go for DED sort of processes where we can go for repairing and remanufacturing significantly. The process parameters, as we discussed in powder bed fusion, DED also has a lot of process parameters which are really, really important in controlling the quality of deposition. The most common process parameters are laser power, or electron beam power, or the arc power. So the power base plays an important role in controlling the energy into the melt pool. Beam diameter, then material feed rate, which is the amount of material that we are feeding into the melt pool, which can be in gram per minute, which can be in meter per minute. Generally, gram per minute is used in terms of for your powders, and meter per minute is generally used when you go for wire-based additive manufacturing. Scan speed is another parameter which gives you the speed at which the laser is moving. Has spacing, again similar to powder bed fusion. It's the overlap between two tracks. So we have one line of deposition. You can see here, if you, the first line of deposition, then you deposit other lines adjacent to this. So what is the overlap between these lines is something known as hatch spacing or the transverse traverse index. Then scanning strategy plays an important role. That's the orientation, the direction in which you start depositing the laser orientation that you are using. Then build direction is the direction in which you are building the parts. It, the same part can be built in a multiple orientation. If you're using a take example of the cylindrical pipe, you can print it in a vertical way or the horizontal way. So it depends on what you want and how you want to get the structure. Again, controlling the process is really important, as I mentioned earlier. So laser density, power density, interaction time plays an important role in controlling the quality of deposition. So if you take this example of powder density and interaction times, you can see that by precise control of power density, laser power density and interaction time, we can move from one zone to other zone. So there's a zone where the energy density is very less and the interaction time is so short. Then we go for heating, and there's a melting zone where the energy density is intermediate to vaporization and heating, and we get interaction time in this particular scale 10 raised to minus 6 to 10 raised to minus 5 seconds. While if you go to very high energy densities and then we go to very short interaction time, then we go to vaporization stage. So these are generally used for material removal applications where we want to interact with the material for a very short period of time. We go for vaporization. So these are how we control the process. So power density and interaction time plays an important role. Interaction time is nothing but the ratio between beam diameter and the scanning speed. So this, by controlling this ratio, we'll be able to control the interaction time in the process, which will be able to control the mode of process as well, whether you're in the heating zone or melting zone or the vaporization zone. Then coming to the next one, so by controlling the energy density, again we can control the zone, the mode of melting that we are doing. So if we are going for the first basic start is a conduction mode where the depth to width ratio of the melt pool is less than 0.4. Then it is the conduction mode. As we move forward, it goes to transition stage where the depth is more as compared to width. Then we go to keyhole mode where the depth is very high as compared to the width of the melt pool. So conduction mode, transition mode, and keyhole mode are the different mode of melting that is seen in ID manufacturing. Then when you start understanding more about the process parameters, there are different combined process parameters which are really important. One is power density, which is a ratio between laser power and beam diameter. So it controls the amount of power that is available per unit area. Interaction time is a ratio between beam diameter and scanning speed, which is the unit is seconds, which controls the amount of time the laser is in contact with the material. Specific point energy, it's a product of area times the interaction time and power density. Energy density is a product of interaction time and power density. So these are different process parameters, combined process parameters, which are used for controlling the quality of deposition. Again, there are other process parameters like laser energy per unit traverse length, which is the ratio between laser power and scanning speed. Material feed per unit length, that is a ratio between material feed rate and scanning speed. Laser energy per unit material feed, which is the ratio between laser power and material feed rate, and nothing but the ratio between the other two factors. So by controlling all these process parameters, we can control the quality of deposition significantly, and we'll be able to produce parts of very high density by optimizing these sort of process parameters. So this is one of the examples. So one of the examples in which they have combined the laser energy per unit length, that is linear heat input, that is joule per millimeter, to powder feed rate. So you can see that either you can go for these two combined process parameters, or you go for this process parameter and go for the individual process parameter later on. Try to develop this process window. So here it is, power and scanning speed is combined here, and powder feed rate is brought here. These are the three most important process parameters in DED, other than if you consider the other parameters like scanning strategy, build direction, all these are important, but the most important process parameters and most commonly used process parameters for controlling the process quality are laser power, scanning speed, and powder feed rate. So the first two, laser power and scanning speed, is combined here, and we have powder feed rate here. So we can see that we have different zones here. So as we go to high feed rates and lower energy density, we have lack of fusion. If you go very high density, energy density, and lower material feed rate, then we go for key holding. So there's a mid zone area where you can find the high density, and at the same time the density is very good. We are not going for unnecessary lack of fusion or key holding. So when do you select both the process? So as I mentioned, both this powder bed fusion and DAD has its own advantages and limitations. We need to understand the capabilities, the strength of this part, processes before we select for any application. So let's take this example of a very complex part which took more than 6 months to be produced by traditional manufacturing. While if you use powder bed fusion for this, it takes fewer than 5 working days. Why I prefer powder bed fusion in this case is because of the geometry that you can see here. So if you see the geometry here, it's very fine featured structure. So the features are in micron scale. We have very highly complex designs in this. So in this sort of cases where the design is highly complex and you want to go for parts which are having lightweight structures, porous structures, we go for powder bed fusion, not the DED process. While there are applications where we go for DED process. So let's take this a comparison example where they try to compare DED and powder bed fusion for a product. So it's done by Optomic. Optomic is a company which produces DED machines. So when they had to produce this sort of part, which is not very complex as compared to the previous design, but it's a medium complex part. And if you want to go for this sort of manufacturing, we have two options: either go for DED or powder bed fusion. And when you select the process, you should bear in mind that time is money. So when you start selecting the parts, if it's medium complexity, if it can be dealt, which can be produced by both powder bed fusion and DED, then you need to have a comparison of cost and time. So when the Optomic did a study and they tried to compare the cost and time required for manufacturing this part, it was it came up that DED requires only 10 hours to produce this part, while powder bed fusion requires 240 hours to produce the same part. And as you know, time is money. So when you convert to cost, the cost of producing the part by DED is very less as compared to powder bed fusion. So the process, the DED is more affordable as compared to powder bed fusion in this particular case. While in the previous case, powder bed fusion was more was a better choice because of the complexity involved in this, but because of the design issues associated with it. While in this case, since the design is not very complex, it's a moderately complex structure, then we can go for DED because it reduces the print time significantly. And similarly, if you go for applications which requires repairing, so this is one of the example of the gear repair case where the 8 week lead time is converted to 1 day. So these sort of repair cases where we can go for DED instead of powder bed fusion. And there are another cases where you need to go for multiple materials. You want to go for a ceramic at one end, we want to go for a metal at the other end. In those sort of cases, again, we need to go for DED. So again, the point I wanted to make it clear here is that if the selection of process is really important, either you go for powder bed fusion or DED, it should be based on the application. And we cannot generalize the selection of the process just by saying that it's an anti-manufacturing process. So the selection is really important. Again, another process. This is another example of a RS-25 power head, which wanted to make this structure, which took more than 90 days. Hello?
Sir, 1 minute, sir. 1 minute. Someone is switched on their. 1 minute, sir.
Yeah, no problem.
I'll mute them. Yes, sir. You can.
Thank you. Yeah. So if you see in this particular example, when you want to make such a structure, powder bed fusion requires more than 90 days using a large platform powder bed fusion system. But in DED, if you go for it, it requires 14 days. So and another example of a nozzle liner which use DED for manufacturing. So these sort of applications where the geometry is not very complex, we can go deal with moderately complex structures, then DED is very much preferred over powder bed fusion. But if you go for high deposition rate, if it's moderately complex, if you want to go for repairing or remanufacturing, then DED is the most commonly used solution. So just sum up this, if you want to make complex shapes, high surface finish and multiple part production, you need to go for powder bed fusion. But if you want to go for a large part size, densification, graded composition or repair works, then you need to go for DED. So this is understanding that we must have. So whenever you select the process for any application, this should be kept in mind. So these are some of the challenges associated with additive manufacturing or DED. So some of them are geometric distortions, where if you see this part, because of the thermal distortion that takes place during the process, we tend to have a deformed structures, porosity and cracking. We will discuss some of them in the later slides as well, but porosity and cracking are one of the major issues of these processes. Large scale structures, when you go for large scale structures, there's obviously, because of the large print time, because of the amount of energy that is getting accumulated, a lot of distortion happens in the material and results in a lot of deviation in from the actual intended dimensions. Processing of reflective materials, processing copper and aluminum is really challenging with laser based systems, so it's really challenging. High surface roughness, and because of the partially melted powders on the surface, and repeatability. So these are some of the major challenges associated with metal additive manufacturing, and some of them we'll be discussing in the coming slides. So if you see the limitations or the issues associated with the process, then if you start comparing it with different criticalities associated with it, so if you see keyhole porosities, lack of fusion porosities, composition change, residual stresses, these are different issues associated with the process, and there are different solutions associated with it, and some of them are critical, some of them are semi-critical, and some of them are non-critical. But we need to understand which one is critical and try to find the solutions for them. Suppose for example, keyhole porosity is one of the cases. Then the first approach is to go for reduced laser power, and the secondary approach can be to increase the laser velocity or go for remelting. Basically, the combined approach is to control the amount of energy that is used for melting. So keyhole porosity can be controlled by controlling the amount of energy used for melting. Again, lack of fusion. Why is lack of fusion happening? So we need to understand the root cause of the problem and then try to find solutions for it. So if in case of lack of fusion, it's basically because of the reduced amount of energy available for melting. So how can we solve this? It can be either by increasing the laser power, reducing the layer thickness, or reducing the laser velocity, etc. So basically, we need to understand the root cause behind each and every issue and try to propose the solutions for that. So I'll just walk you through some of the case studies which I have done, some of the works which I have done in India as well as in abroad. I'll just quickly go through that because considering the time limitations that we have. But if you have any questions, we can have further discussions. So the system which I use in RRCAT, you'll be seeing most of the system when you listen to Professor CP Paul's lecture tomorrow. But this is a system that I use for some of my research activities at RRCAT. So it's a 2 kilowatt fiber laser based DED system which uses a dual powder feeder. We have operator console, a 5-axis station with a coaxial powder feeding nozzle, and a 2 kilowatt fiber laser. Build volume is 250 by 250 by 250. One of the case studies which I wanted to present here is the large scale heat exchanger structure that we try to develop with the DED system. So major problem with this process was material. Again, the material was a new material which is developed, which is Hestel X, which is being used a lot in conventional manufacturing. But there was no study available in literature on additive manufacturing of Hestel when we started this project. So this was one of the first studies on additive manufacturing of Hestel X, which we published in 2019, it seems. So we published on developing the process for this material. So it's a crack sensitive material, and we need to develop this large size structure by using DED based additive manufacturing. Just give me a second. So what we did was we went into the process development. We developed wall structures and bulk structures from this, and then we developed a strategy for developing the heat exchangers. So you can see here, this heat exchanger has bulk structures and wall structures in between them. If you see the solid region is a bulk region, and the wall region is a thin line samples that you can see in the between. So it's basically a cross flow heat exchanger. So you have fluid coming from one side and the fluid coming from the other side, and these are separated by using this bulk structure. So we did a comprehensive study on developing the process for this material and developing how to print high quality bulk structures by using this process. So we started off with normal single track deposition of developing the process for this, and then we analyze them into different categories. So it can be discontinuous, continuous, or crack deposition. Basically, the Lower energy density resulted in discontinuous deposition. Higher energy density resulted in crack deposition. So we selected the intermediate range, which gave us the continuous deposition. We tried to correlate the quality of deposition with the process parameter. So one of the combined process parameter which we defined for this study was laser energy per unit powder feed. So LEPF was defined there. It's a ratio between laser power and powder feed rate. So when we have this range of 8.2 to 13.2, we could get continuous deposition. But as we deviated from that, we got discontinuous and crack deposition. We use a scheme for making thin walls. So you can see that how energy density plays an important role in controlling the quality of the thin walls. So thin walls are really important when you go for thin feature fabrication, when you want to go for repairing applications, when you want to make turbine blade sort of structures. Thin walls are really important, and thin walls are of really good interest in additive manufacturing in powder bed and DED. So as you move forward, you can see that the energy density plays an important role in controlling the height of the deposition and also in the controlling the width of the deposition. So we did some analysis on the wall structures, and this is how a typical bulk structure looks like. So this is a multi-layered, multi-track bulk structure, typically made of DED process. So it's a DED built Hester-like structure. Then we analyze the density of the part. We use Archimedes density analysis and as well as optical microscopy techniques for characterizing the quality of the deposition. We could see that the density is close to 99.5% with some lack of fusion pores at isolated locations. Microstructure is more columnar growth was seen. We had a mix of cellular and dendritic growth. And as we moved from bottom layers to top layers, the grain size was increasing, basically because of the variation in the cooling rates. And we can also see from the EBSD maps that there's a slight texture in the 100 plane as we in the microstructure. And if you see, compare the mechanical properties of DED built part lies between powder bed fusion and DED. So this is not a typical case. Most of the cases we could see that the DED built mechanical structures, mechanical properties lies in between conventional built parts and powder bed fusion parts. Powder bed fusion parts tend to have a higher mechanical strength because of the faster cooling rates associated with the process, while conventional parts have a lower hardness values basically because of the slower cooling rates associated with it. Again, depends on the what sort of conventional manufacturing technique you are using. But if you generally have a comparison, it is inferior to DED is inferior to powder bed fusion and slightly ahead of conventional manufactured parts in terms of the mechanical strength. But if you see the ductility part, if you see that yield ratio is nothing but a parameter which is used for comparing the ductility. So a lower value of yield ratio means that the ductility is very high. So if you see conventional manufacturing parts have a lower yield ratio as compared to DED and powder bed fusion. So we can see that the ductility of DED built parts lies in between powder bed fusion and conventional manufactured parts, while PBF has a higher strength as compared to DED. Then how to control the micropores and non-homogeneous deposition. So we used a technique called layer by layer remelting for controlling the density of the part. So we used laser melting during the deposition after each and every layer, and we could reduce the porosity significantly. We could reduce the surface roughness significantly, and we could also refine the grain structure and change the textures a bit from more oriented in the 100 plane to a more random texture we could observe. And at the same time, the mechanical strength values improved after we do the remelting process. We also did some solution heat treatment just to bring the microstructure more homogeneous. So as you can see, the fine grain structure is in the as-built samples. After heat treatment, we went to solution heat treatment, which is a recommended heat treatment technique for this material. So after heat treatment, we could make it more randomly oriented grain structures. The mechanical properties were brought very close to the conventionally built samples after the heat treatment. And we can see we did mechanical strength test from room temperature to very high temperature, and we could see that after heat treatment, the mechanical properties are very much similar to conventionally built samples. So by doing a heat treatment, by doing proper processing, we can control the quality of deposition and we can control the mechanical strength as well. So when finally we wanted to make this heat exchanger out of it. So we did a lot of trials. So we started with some failed channels. You can see that. Then we went into some channels which are open from both the ends. We could successfully make the channels after a lot of optimization and trials. So these are some of the channels which we made out of it. Then we developed the program out of it, and we developed a proof of concept, and we made this large structure which took more than a month to manufacturing. It was a size of 200 by 200 by 200 millimeter cube. Again, I have worked on number of functionally graded materials. So as I mentioned, DED permits you to go for multiple materials. You can change the composition from one end to other end by varying the composition. So we can join multiple materials at the same time. So copper nickel was one of the cases where we worked with IIT Kanpur and IPR. So we had a copper substrate onto which we added nickel material. So we gradually change the composition from copper end to the nickel end, and by changing the composition of copper and nickel from 100% to 0%. Similar work was done in Delera 50 in stainless steel. We changed the work material from Delera 50 to stainless steel by gradual change in the composition. You can see how the composition of the nickel was changing, and how you can see how the composition of iron was changing from one end to the other end. So if you see at the nickel alloy and the composition nickel was very high, and at the same time at the stainless steel end the composition of iron was very high, and we had a gradual transition as we moved from one end to other end. Then recently we did a work, one of our colleagues at Arackal, we did collaboratively on this particular project. We worked on copper and stainless steel work. So we tried to have a copper and stainless steel FGM. So we try to vary the composition of copper and stainless steel from one end to the other end, try to understand how this composition is affecting the cracking. So when the major issue with copper and stainless steel is that both then doesn't have a good mixing. So they have phase separated morphology can be seen basically because of they cannot make a solid solution. So we can see that thin trapped copper films are seen, and they tend to get try to make cracking. There's a cracking tendency because of the copper films which are formed, and this because they cannot take the residual stresses that are generated during the process. Can be worked on joining copper and stainless steel by thin wall fabrication as well. We joined copper and stainless steel and at different gradation of 50% composition or 100% composition or 20% composition. We could see that there's a gradual change in the composition and the micro hardness values as we move from one end to other end. If you start comparing the mechanical strength, pure copper has got a good similar property as compared to direct joint structures, but 50% joining gives you similar structure. But if you have 20% grading, because of a lot of micro cracks involved in the process, because of the continuous thermal cycling that happened during the process, this mechanical strength reduced significantly. We also worked on doing some laser post processing, which is a laser polishing on additive manufactured part. So this is an as-built part. You can see the surface topography. We developed a laser polishing processing window. We developed laser processing parameters for that. We did some modeling on controlling the how to understand the depth of the melt pool with respect to different process parameters, and we had a comparison with experimental values. So we compared the melt pool values at different energy densities with experimental values, and at the end we came up with a two different regions for doing laser remelting and laser polishing. This is really important. So when you if you want to go for shallow surface melting, if you want to go for high quality polished surfaces, we need to work on the shallow surface melting region, not on the surface over melting region, which is SOM region. So this again shows you the importance of selecting process parameters properly. So if you're selecting the laser energy density in such a way that we remain in the shallow surface melting region, we can control the depth significantly. Again, if we want to go for higher depth of melting, we need to go for surface over melting. But again, the surface over melting results in higher surface roughness as compared to shallow surface melting. So we need to have a proper understanding of how to vary these process parameters so that we can get the required surface finish. Then I would like to show some of the works which I did at University of Waterloo in Canada. So I worked at multi-scale IT manufacturing lab, and this is one of the systems that we use for the project. So we use a 1 kilowatt laser-based DED system, and this is a powder morphology that we use. We had dual powder feeder there. We had a front of a nozzle. We have Xeris weld camera. We use a 1 kilowatt fiber laser and the laser line scanner for scanning the surface of the parts. So this is the overall system that we used. We did some case studies with that. So major aim was to develop certain processes which can be used for industrial applications. So we developed overhang structures like dome structures with this process. Then we worked on the surface quality integration, geometrical analysis on how the CAD to part variation was there. And we could see that overall the geometrical stability is very high as compared to like the top surfaces has a higher deviation, but the overall average surface deviation is very less. We also did an interesting work on overhang geometry by using a bending pipe structure, which was published in Additive Manufacturing Journal. So what we did is we varied the scanning speed within a layer. So if you start slicing this structure, we can see that at one particular side the layer thickness is lower and the other side the layer thickness is higher. So that means that within the single layer we need to change the scanning speed. So we need to control the scanning velocity during the deposition in a single layer itself. So you can see here how the velocity has moved from one end to the other end. So we have a region where the lower layer thickness is there. So we went with the faster scanning speed there, and the region where we need a higher layer thickness, we went to a we went to lower scanning speed there. So based on that, we varied the layer thickness within a single layer, and then based on that, we then did a part to CAD comparison to understand how the deviation is there. So the maximum deviation was within 0.5 millimeter, which is acceptable in the application. Also, the microstructure, if you see, the region which went to higher scanning speed has a very fine grain structure, and the region where we went to lower scanning speed has a coarser grain structure, and of course it influences the micro hardness as well, but not in a very significant way. So if you see this, so based on the scanning speed we can control the microstructure, and then we can control the mechanical properties as well. So it's another project which I worked on. We developed laser cladding. So the project was on to developing a alumina forming steel cladding layer on stainless steel tin wall tube. So we had a tube which is 0.5 millimeter thick and just very thin so that it get damages with laser. So it's very challenging to deposit something on a thin wall tube, because if you go for thin tubes and we start cladding on that, the tube get damaged significantly and we impinge laser onto the surface. So because of that, we use some external cooling mechanisms. So we use argon cooling externally to deposit the clad layers on the surface. So initially we did without any clad layers, without any external cooling, and we could see that the deposition was getting damaged inside. So we could see that the inside tube was getting damaged. But as we moved forward and we started using external coolings, we could control the quality of deposition. We could deposit the clad layers on the outside without damaging the tube inside. So these are some of the samples that we prepared, and this is how the cross section looks like. So this is another application of DED. So what I was trying to explain is the new application. So another advanced application where we can control the layer thickness and we can control the energy density in such a way that even we can go for cladding on thin wall tubes which are used in the nuclear sector. So this is another challenging project because of the thickness of the part, and we can see that there is no defect formation within the um deposition, and there's a gradual change from the tube to the mixing zone to the clad zone, and we can say that the gradual change in the hardness as well. So this is alumina forming steel, which is a highly corrosion resistant material, which we have sent to further evaluation for the corrosion and corrosion analysis at the user end. This is another project that we worked on, predicting the geometry control. So we worked on, this was one of my colleague. I was part of the team in which we developed a process for predicting the quality of the part. So we use deep learning based techniques for predicting the surface defects. So we could generate convex shape. We could predict the convex structures, concave structures on the sample structures. And then we developed a methodology which can be used for controlling the quality. So if this is the as-built condition of the part, and by controlling the scanning speed, controlling the laser power during the deposition, we could control the quality of deposition. So you can see that how the part was initially, and then as we moved forward, we could improve the quality of the deposition significantly. This was done by controlling the scanning speed and controlling the laser power. So again, I was working on the material characterization part of it. So we could see that the density of the part is very high, even though, so major concern from our end was, since we are playing with the laser power and scanning speed, are we going to hamper the surface quality or the build quality of the parts? So when we went to the cross-section analysis, we could see that we didn't hinder the mechanical properties or the density of the part significantly, even though there was some amount of porosity was higher in the laser control samples. Overall, if you see that the quality of the deposition was very high, and we could get very high quality structures at different conditions. And the microstructure was also similar. The cellular structures were seen on all the samples, but at the same time, in the laser control sample, we could see slightly finer grain structures. And this was observed in the hardness map as well. We could see some peaks for the hardness maps in the laser control samples, but overall the hardness was almost similar. So we could control the geometrical quality of the parts, but without hampering the mechanical strength. And some of the ongoing research works, I'll just quickly go through this. And I was working on Inconel 617 at the moment. Some of my students are working on it. So we are trying to understand how the Inconel 617 process affects the surface quality and the build quality and the porosity. So we could understand that we built blocks at 3 different energy densities. We could see at a lower energy density, the density of the sample was fine, but as we move to very high densities, the quality of the samples degraded, mainly because of the cracking that happened and because of the higher residual stresses. And we could also control the mechanical properties significantly. We could see that by controlling the energy density, we could control the dendrite arm spacing, which can help us to understand the cooling rate associated with the process. So by varying the energy per unit length, we can control the cooling rate, and by controlling that, we could measure the dendrite arm spacing, and we could control the energy density. So again, the EDS maps showed that it is more homogeneous. This is very unlikely that's happening in DED. Generally, in DED process, we tend to get very non-homogeneous composition changes, because we try to have a lot of segregations involved. But because of the lower scanning speeds we are using, so if you can see in this table, we use very low scanning speeds in this, which resulted in very homogeneous and a homogeneous grain structure, sorry, composition of materials. And again, EBSD gives us the orientation of the grain structures. Could see that as we move from top to bottom, there's a bottom structures and the top structures. We could see that there's a orientation preference along the 100 plane across all the samples. And we can also identify the cracking that happens during in the overlap zone. So we could see that how the overlapping is working here. So if we go to high energy density, the overlapped region, whenever there is an overlap between the layers, overlap between the tracks, we could see that there's a cracking that is coming up. Okay, we understood the mechanical behavior of this material at different conditions, and it was found to be higher than the conventionally built samples. We're also doing some bit of works on polymer TPMS structures. So some of my students are working on different TPMS structures, controlling the density of the TPMS structures, and controlling at how different TPMS structures can yield in different mechanical properties. So we are working on those structures at the moment. We varied the porosities, we varied the type of TPMS structures, and how can we change the energy absorption capabilities, because this is one of the applications in automotive structure. We want to increase the energy absorption capability of the material. So by varying the different types of TPMS geometry, and by controlling the porosity of these parts, we can control the energy absorption capability. This is one of the interesting work that's ongoing at the moment. We're trying to develop 3D printed back support for wheelchair users. So we used a body scan of a person, then we scanned it, we converted to 3D model, and then we 3D used it. We collaborated School of Health here. So there's a physiotherapist in School of Health who gives us the instruction on how to modify the design to meet the user requirements. So now we are working on this project. We are trying to develop these sort of wheelchair structures which can be attached, these structures which can be attached to the wheelchairs, which can improve uh, the user experience and how we can provide more comfort to the wheelchair users. So as a conclusion to the project, to the discussion, the challenges in metal additive manufacturing and the opportunities: challenges, shortage of qualified materials. We need to develop more materials because, as you know, conventional manufacturing has got a lot of material portfolio, while metal additive manufacturing has limited material portfolio. We need to improve the material portfolio of metal additive manufacturing. Speed and productivity is a challenge. Repeatability and quality assurance, industry-wide standards need to be produced. There's the need of end-to-end workflow integration. Softwares are limited. We need to develop more softwares which can help us to control the quality of deposition. Security and skill set gap. Opportunities, there are a lot of opportunities in terms of machine and software development. So we can understand that a lot of incubation sort of activities are going across the country on machine development. A lot of companies are coming forward in developing make in India machines and all. So machine development is an important aspect because still we rely on very limited machine manufacturers for 3D printing. So research in this direction is really good. Process development and control, material feedstock development, design for AM is an area of work, modeling and simulation, characterization of testing, quality control and assurance, application development, education and training. That's why we are doing these sort of FTP programs. Some of the research areas at the moment in my lab, we work on laser DED of nickel superalloys, characterization of these structures and metallurgical analysis. Design optimization, so we work on design for AM, work on TPMS structures just for lightweighting of aerospace structures. Additive manufacturing for hydrogen applications, so recently I'm getting involved in a UK Iceland project where we develop materials for hydrogen applications. We test materials for hydrogen applications. So it's an area of important area of working. Post processing already manufactured parts and wire arc additive manufacturing and metallic alloys. So we're trying to develop some multi-material structures by using wire arc additive manufacturing at Teesside University. So as a conclusion, AM is an advanced manufacturing technology used to build complex components in a layer by layer fashion, started from rapid prototyping of polymer materials, extended to metal AM for industrial applications. There's a careful material and process selection required for successful AM implementation. Various case studies shows the benefit of this technology in different sectors. We require systematic investigation and training for high quality parts to be produced by AM. Research opportunities are still plenty to improve the process. There are some of the special issues which I am co-editing at the moment. So if you have any publications which you'd like to submit to these special issues, feel free to contact me. One is in sustainability in a Q&A journal, and then we have frontiers in manufacturing technology and frontiers in mechanical engineering, where we have a special issue on recent advances in quality control of metal additive manufactured parts. Thank you.
Thank you, Professor. Now the session is open for question and answer. Any questions from the participants?
Good evening, sir. I have one question.
Yeah.
Sir, actually, would you suggest some efficient techniques for measuring residual stress in metal additive manufacturing parts, sir? Apart from X-ray diffraction method?
There are methods like hole drilling methods. So basically, you drill a hole, and based on the size of the variation in the size of the holes, you can measure the strain accumulated in the material. So hole drilling is another example. There's a very good review paper on that. I can, if possible, I'll share that as well. Like there's a very good review paper which reviews all these different techniques. But other than XRD, the most commonly used techniques for measuring residual stress in additive manufacturing is a hole drilling method.
But if the part future size is very, very small, sir, then how to implement this hole drilling method, sir?
So what sort of size are you talking? Like this sort of hole drilling is in micro scale. They generally we use something like a wire radium sort of structure systems for that. So we can go into very small holes, not a drilled hole actually. So it can be very small holes as well, but I don't know the feature size that you're talking about.
Okay, sir. Actually, the feature size is 20 mm, sir, in all the sites.
So with that, it's possible. Hoteling is possible.
Okay, sir. Similarly, in DED,
Yeah.
is it possible to integrate in situ reinforcement, sir, during the process?
Yeah, sure. We have worked on different projects on that. So I worked on projects where we used tungsten carbide particles during the deposition. Recently, we are doing a project in which we use titanium carbide into nickel superalloy. So this is possible. Yeah.
Thank you, sir.
Thank you.
Any other questions from the participants? Sir, we have
has been posted in the chat box.
Chat box, sir. Sir,
We read in the chat.
yes, sir. I'll tell the question, sir. By joining two similar materials like titanium and steel, the interlaminar shear stress will affect joining process. How can we eliminate the effect during fabrication? This is the question asked by Dr. Santosh.
Yeah, so whenever you go for multi-material joints, there are two ways of doing it. One way is to gradually change the composition from one end to other end. So if you have titanium and steel, just taking the example of titanium and steel, but it's not possible to join them in this way. But if you have two materials A and B, if you want to join them by using additive manufacturing, by using a functional integrated structure, you can start from A material to B, go from 100% A to 0% A and 0% B to 100% B. So we can just gradually change the composition from one end to other end. This will help us to control the inter layer issues to in a significant way. And if there are materials which cannot be joined in such a way, and if we can bring a third material into it which has thermophysical properties or thermal conductivity in between both these materials, so that we can control how the deviation happens, or we can control the the transition significantly. So just by bringing a new material, sandwich material in between the A and B, we can control this sort of stresses that is generated in the process.
Sir, I have one question. How to cut
Yeah.
out the cost? So because there is a metal additive is too expensive. So what's your opinion, sir?
So it's costly. I agree to your point. It's very costly, but there are processes which are not costly as well. As I mentioned, there are processes like, so I understand where you're coming from. For general research, accessing to a metal additive manufacturing facility will be a really costly one. So the one of the ways is wire arc additive manufacturing. It is nothing but an extension of your welding. So it is one of the cheapest system that you can make for making metal additive manufacturing systems. So you just need a welding torch. You can have a control system. You can have wire feeder. Then you can make a wire arc additive manufacturing system. You can attach the system to a CNC or attach the system to a 3-axis workstation or to a robot. Then you can make a metal additive manufacturing system, which is not very costly as compared to laser electron beam sort of systems. Another approach, if you want to work on metal additive manufacturing, is the indirect way of working. So if you go for, there are systems which can print. I mentioned about the indirect metal additive manufacturing, where we can go for polymer and metal mix, and then later on do some post processing on that to remove the polymers and get the metal joined together to make high density parts by doing infiltration or by sintering. So these are some of the post processing that can be done on these parts to improve the density. So by going for such processes, this is one way. Other way is going for wire arc additive manufacturing sort of processes, which can be used for making large scale structures. A lot of research, a lot of people are using wire arc additive manufacturing across the Europe and US, mainly because of the low cost involved in it and because of large scale structures it can make other than powder bed fusion. But if you want to reduce the cost of making powder bed fusion, the best way is to go for producing the system by yourself. So that's, as I mentioned, maybe tomorrow you will get more clarity on that. Professor CP Paul is heading the incubation center at Arackal. So you work a lot on system development and selling the system and incubation activities related to the systems. So I think you'll get a fair idea on how can you control the cost of these systems by listening to the session tomorrow. But in my opinion, the best way to control the cost is by developing system by yourself rather than relying on the foreign market.
Thank you, sir. Thank you.
Hello.
Hi.
Sir, I have one question. That
Yeah.
you have discussed about the remelting of each deposited layer. So, how can we remelt with a laser? Is there any kind of hybrid kind of machine that is attached to that? Or suppose in ORR machine, we can attach one laser with it that can follow the path, or in which way we can do that remelting?
Yeah. So the one that I did, it was a laser DED system. So it was easy. I just had to turn off the powder. So after each layer, I turn off the powder for the next layer, and then remelt. The laser is turned on. The laser remelts the material again. When I go for the next layer of deposition, I turn on the powder again, and the deposition happens. But in the case that you mentioned, in case of wire arc additive manufacturing, yeah, the laser can be attached in situ to the same system. So after each, so you might have seen hybrid machining systems, right? Hybrid AM systems which uses DED plus CNC machining. So instead of the and along with the laser, along with the machining system, you can have a laser attached to it, which can be used for melting after each layers, which can control the geometry. So we have worked on a project in which we use laser marking as a tool to control the mill pull feature size. So this was done in situ during the process.
Thank you.
Thank you.
Thank you, Ravi bhai. Yeah, we are exceeding the time, sir. Shall I ask the question posted by participants, or we'll close, sir?
And it's okay for me. Otherwise, if you
Okay,
want
okay.
have any
No,
other
no issues, sir. We have no issues.
it's fine
Yeah.
for me.
Yeah. Yeah, Ritvik asked one question. Can you please comment on the challenges associated with support structures?
So support structures are generally used in powder bed fusion, not in DED. Because DED normally we have the 5-axis configuration, we have the robots which we are using, so we don't generally go for support structures in DED based additive manufacturing. But in powder bed fusion, yeah, we end up in a lot of supports which is challenging to remove, and generally we use wire EDM as a technique for removing these support structures. And basic challenge associated with support structures is the distortion that it can bring to the original part while removing the support structures. And we should be able to design the parts. So this has to do with design for additive manufacturing. So when you're designing the parts for additive manufacturing, you should make sure that the amount of support required for your product is really less. So you should select the orientation, select the design in such a way that you can control the amount of support required for the part. At the same time, if you see, for example, if you take some channels for pipe flow, if you take circular channels or square channels, you end up in requiring support structures. But there are certain designs which are self-supported designs, like diamond shaped structures, which are self-supported designs. So if you go for self-supported designs, then you can control the amount of support structures required for the application. So these are some of the things that you need to keep in mind when you go for the sort of support structure optimization. But again, in DED, we don't require support structures, but in powder bed fusion, we need it. Yeah.
Yeah, Arun Prakash asked one question. Types of post-processing techniques for LPBF and its effect on microstructural mechanical properties. I hope your book will address these techniques and the effect.
I've covered some of them, like I've covered heat treatment. I've worked on laser shock peening as a post-processing technique where we try to do shock peening after additive manufacturing to impart compressive stress into the material. We worked on laser melting to improve the surface quality, surface finish of the structure. So there are different post-processing. Again, there is no one answer to this. Depends on the application, depends on the requirements. Yeah, there are certain post-processing which can be used only for surface finishing. But some of them can be used for tailoring the microstructure. So it depends on the application. I think you are muted.
Yeah. Next one is by Paul Mukund Mishra. What are the challenges you have faced during printing of copper?
Yeah, the most important challenge is the reflectivity. Copper is, I think, more than 95% reflective to fiber laser. So it's really challenging. So finding the right optimized window is a challenge here. So I was working with one of my colleagues in Arackal. His name is Sunil. So we are trying to develop the process for copper. So we had to develop a lot of strategies. So we use single laser power. We varied the laser power from low value to high values. So we changed the process parameters a lot. We need to end up in a lot of process optimization. The major challenge is the reflectivity and thermal conductivity. Creating the mill pool itself is a big challenge in laser systems. when I did one of the postdocs, I had to work on a 1 kilowatt laser for copper, which is really challenging. Then the worst challenge was working on a 500-watt laser for like copper, because then I had to go for different coatings on the copper wire to improve the surface, the absorptivity. So we went for black coatings on the wire to increase the absorptivity of the laser. So these are some of the challenges associated with using copper and lasers, especially when you go for lower laser powers.
Yeah, next question is by Santosh. How to control the compressive stress during metal 3D printing?
Generally, the compressive stress is not a problem. It's a tensile stress that is creates problem. So tensile stress are normally eradicated by using laser shock peening. We can do heat treatments for controlling that, but normally the compressive stress are friendly, so we don't have to eradicate them. That's not of a challenge as compared to tensile stresses, but tensile stresses are generally avoided by using short peening or laser shock peening.
Yeah, Mayalagan asked one question: is nickel-based alloy is suitable for warm?
Yeah. We can find a lot of papers on nickel superalloys and MAM. A lot of inconel grades are being worked on MAM.
I hope these are all the questions asked by the participants.
Thank you.
Thank you, Professor. I would like to extend my heartfelt thanks to Dr. Jinoop Arackal Narayanan for readily accepting our invitation and delivering an insightful session. Your contribution was invaluable to the research community, sir. Thank you. A special note of gratitude to our chairman and our management people, our HOD and colleagues. And I also want to thank our participants. Without you, this program won't be this much successful. Thank you, sir. Thank you all.
Thank you.
Thank you, sir.
Thank you. Thanks for listening to me, and feel free to contact me if you
have any doubts. Yes, sir.
If any of the participants want to discuss about some opportunities or research or anything, feel free to contact me. I think you have my email address. You can share with the participants as well.
Yes, sir. Sure, sir. Sure, I'll do. Thank you. Thank you, Professor.
Thank you. Thanks. Bye.